Hello, Dr. Anna and Professor Vivian. Thank you so much. Today I'm going to discuss about my research, the progress and what I did. And as you know, as per our meetings, we try to improve it so many times. So there is a presentation also in the coming 15th of November. So in this I would like to use this opportunity to let you know the progress and what I did until now. So as you know, this is comparative analysis and design of 44 and 100 story multi-purpose high-rise RC building using performance-based design procedure and Ethiopian prescribed adopted RC building design code. This is my topic, as you know. So if you remember, the main idea is that prescribed adopted code and linear analysis of structure is not adequate enough to answer structural needs. So what I am intended to do is that most countries, especially Ethiopia, should transfer from code-based static design procedure to performance-based design procedure, and that is the whole idea. And what I am going to do, I want to show you what I did until now. If I open, as I told you, we have classical model analysis. Again, I perform time history analysis and response spectrum analysis. These three analyses are done on linear model, okay, and linear model and non-linear modeling in non-linear time history analysis and pushover analysis. I will do that as well. So a total of 5 analysis will be performed on our sample models. So for example, let me open the 2 samples. I am going to use ETAPS, as I told you. I am going to use, for this research purpose, I am going to use ETAPS, but I have also this Perform 3D. This is Perform 3D. I have version 7 and version 6 as well. After this, because I have time in the future, I will incorporate the whole analysis with Perform 3D as well, because Perform 3D is best for non-linear analysis. But ETAPS, it works, but it's not like Perform 3D, because Perform 3D from CSI, they use it for non-linear analysis only. So let me open the, for example, let me open the first one, classical model analysis. I will come now I will show you in a minute what I did on it. So what as I told you, I perform classical model analysis, response rate analysis and time history analysis, and I will compare the results for global and local responses until it opens. Let me show you some of the results which for 44 story building and 100 story building I perform classical model analysis, and I have the results just until the software opens, because it will take some time. I have these are the mode I did on classical model analysis, and until it opens. Let me show you. I have a video for each 20 modes. Okay, for each 20 modes I make video. And I will explain why I did classical model analysis, what is the benefit, what is its usage, because in our research it is very important part of analysis. Okay, this is 44-story building. This is 44-story building. So this is 44-story building, just a normal kind of building. I just choose as a regular type of building. It's a regular type of building, not that much. As you can see, it is symmetric, and I just use 4 places, just lateral earthquake resistant systems. I just use 4 places only, and we have core hole here for the lift purpose, and it's a regular kind of building, not that much difficult. And just to come here, so these are some of the translational movement, the reaction. I will explain this in a minute. So just to for this building, as I told you, the material, just steel reinforcement, all as per the code, it is defined here. Okay, it's defined here, and steel also is defined. Material property for 44-story and 100-story building, it's already defined. And for load cases, we have dead load, live load, and modal, and this one also imposed load. Modal analysis, I just assign it 20 here. Maximum number of mode I use is 20. We can increase because the number of modes is equal to number of degree of freedom, but I choose to just make it 20. And this is modal analysis. This is eigenvalue, and it's also there, but eigenvalue analysis is used. And I included also p delta analysis. So before I came to the analysis part, this is for 44-story. We have also 100-story also. This is 44-story. The 100-story is this one. This is for classical model analysis. So I have 100-story also. So for all analysis, we have 44-story and 100-story. Classical model analysis, I have 44-story and 100-story, and this times 3 analysis also. I have 44 story and 100 story. The same thing for nonlinear times 3 analysis. We have the same 100 story and 44 story, and I will come in a minute also for how to get ground motion from peer website. I extracted already 11 for our analysis. I extract 11 ground motions from peer websites. This is real earthquake. Let me open it. This is real earthquake data. We will use it for our linear and nonlinear times 3 analysis. As you can see, for example, this one is peer NJ strong motion data base record. This was Imperial Valley 06. This is a station. This was recorded in 1979. Zero operator 147, acceleration time series in units of G, and total points, all these total points are around 6,382, and the interval is 0.01 second. So as you can see, each row have 5 data. 1, 2, 3, 4, 5. We have 5 data, and we will use this data later. Okay, we will use all. I extract 11 ground motion. This is only one data, but I have also a lot of data. Around 11 I extracted. Lenders, Imperial Valley, Lenders, Chutes, and others. We will see how to scale this earthquake for our target response spectrum for our site. I will come. So we have pushover analysis also. The same thing, 44 story and 100 story, and lastly, okay, that's all. This is the 5 classical model analysis, linear times 3 analysis, non-linear times 3 analysis for verification. This is a pushover analysis and response times 3. This is a RAC analysis, response spectrum analysis. 5 analyses. So as per my, now let me go to, this is 100 story. It's open already. This is also regular type of building, and regular type of building. All material property, loadings, you see, this is also 100 story building. So both 100 story and 44 story, we will use it for our analysis. Sorry, I just because it is a 100 story building, it needs the memory. Okay, so this is for 44 story building. So let me go to our presentation. This is our presentation. Now I think you get some idea. So we have the models, so all definitions, material definitions, section, all frame sections, whatever frame section we use for our sections, column, beams, and shear walls. Everything is defined, and our mass sources also defined. This is a mass source we have, because now it's already run, it is closed, that's why we cannot. Load cases, our load cases, dead load, live load, modal. For modal I use 50, just I set it 50, that's enough, because we don't need all the higher modes reactions. We need only, as per code, 80 up to 90% of the mass participation factors. That's why 50 is too much. Around 7, 8 it will achieve. That's why I choose that. Load combinations. Now we don't have any load combination, because because we are going to make classical modal analysis. So the whole idea is comparative analysis and design of 44 and 100 story multi-purpose high-rise RC buildings using performance-based design procedure and Ethiopian prescribes adopted RC building design code. So we have these models, because this work is already new. I am doing from scratch. I will come up after literature review, and I will show why this work is original. And so let me continue. Contains, for example, background, literature review, methodology, finding, conclusion. So the background is adopting seismic design code without necessary amendment has enormous negative impact on the overall performance of a structure. This is the main idea of my research, because most countries, they just simply adopt, as you know, there is ACI codes, UBC 94, 97, and IBC 2000, and so on, Indian's code, Japanese, and others. So some countries directly adopt the code and they just use it for themselves without amending it. This is the first thing. The second thing is, these prescribed codes, they use only linear analysis, linear static analysis. So this one also doesn't consider the non-linearity of the structure. So in our case, I will show you, this is linear models. This 100-story and 44-story buildings, they are linear models. This is linear model. For pushover analysis and nonlinear time history analysis, we are going to change these models into nonlinear by fiber modeling method. When I explain all step by step, because I am planning to prepare 5 videos on each part. Okay, today the idea is, after I explain why I am going to do this research, the idea is, in this video I am going to show you only the classical model analysis, the modeling, the application, the modal cases, and the outputs, and why classical model analysis should be done. That is the idea. Then every video, as per my analysis, I am going to have 5 videos. Then each video will explain each steps. So for pushover analysis and nonlinear time history analysis, I will show you, I will explain in that video how to extract the earthquake data from peer websites, and how to scale it, match it for our target design response spectrum. In that time, I will explain what is plastic hinge modeling, how we will assign plastic hinge modeling for columns and beams, and fiber nonlinear modeling approach for this shear holes. In that time I will explain. So let me come here. So the background is clear now. Countries are adopting different codes, and they are adopting it without amendment. Even if they amend it, it is still linear analysis. That means it doesn't consider the nonlinearity of a structure. So performance-based design is a cutting-edge seismic design technique that has been extensively used for seismic assessment of existing structure and the seismic design of variety of new tall buildings. This is the main idea of my research. My research starts from here, then it will go further. So my research questions. The first question: the seismic performance of reinforcement concrete structure designed according to Ethiopian standard 815 corresponds to Eurocode 8 2004 standard based on EN European norm 1998-1. Seismic code recommendation is effective or not effective? This is first question, because we adopt it, even if the name is Ethiopian standard 8, it is directly the same as Eurocode 8 2004, and it is also the same as European norm 1998-1. So this is effective or not effective? This is the first thing. The second thing: does the comparative nonlinear times 3 analysis push over nonlinear analysis on 44 and 100 story RC building and current Ethiopian adopted code linear analysis such as classical model analysis, response spectrum analysis, and linear dynamic times 3 analysis? We selected 11 ground motion as I showed you from peer website. Result is the same or different? This will tell us, it will show us the shortcomings and the problem with our adopted code case, not only in Ethiopian EBCs is 15, but all over in the world, because adopted codes and linear analysis is not adequate enough. We will see that also in the research literature review. Also there is a lot of works done to show the difference between different codes, Indian codes with the US code, US code with the British code, even if the codes themselves are not the same. So most researchers, a lot of researchers, they did a lot of comparison works, a lot of designs with prescribed codes as well as performance based design method to check which one is economical, which one is effective, and so on. So we shall see this one. The third one: if the code states that modal force and shear combined using SRSS shall scale up to as required to 85% of ELF base shear observed from the response spectrum. After ELF analysis, basically one of the limitation of this research is I will not incorporate ELF in this study. But as per code, it says once you get the base shear acceleration from ELF analysis and time history analysis or response spectrum analysis, once you get the result of base shear acceleration, you have to check it with linear ELF analysis, and if the result is low, then you have to scale it up. So my question is, what was at the end of the day? We will answer it, because I got the answer at the end of the day, at the end of my research. But this is a question, because always when we did dynamic analysis, the result is always lower than the ELF base shear design result. So we shall see this also. Number 4, for our design site, how do we select and modify different ground motion for linear and non-linear response history analysis from peer ground motion database, the Pacific Earthquake Engineering Research Center, and USGS and other website, and match it using the well-known software SeismoMatch 2016, RSP Match, and ETAPS 2009. All basically for this research I use ETABS 2019 and I match the ground motion I showed you. I match it with a target response spectrum with ETABS 2019. But we can use also Seismo match. But my Seismo match, let me show you. I have Seismo match, but my Seismo match is a student version, and it works only until time period of 4 seconds. Okay, it works only 4 seconds, so it doesn't work for me. Where is it? Seismo match. It was here. Okay, I will show you. Okay, no problem. I will show you when I reach into the time history analysis, because we have to match the ground motions, and how to match it and how to fix it, I will show you there. Okay, let's continue. So the objectives of this study are to investigate the principal risk of adopting other countries' codes without proper amendment to local typical geological behavior in designing and construction high-rising building in Ethiopia. Okay, now I say in Ethiopia, but all over in the world. To investigate the potential benefit of a lesson learned from the design of a high-rising building using the PBD approach over prescribed adopted code. So there are a lot of buildings which are designed as per PBD. So what is the advantage over adopted codes for the use of local consultant and contractor from Ethiopia? To investigate strategic guidelines to take advantage of design output of this paper. Now, new generation of PBD approach, nonlinear dynamic analysis. This is nonlinear response history analysis or nonlinear time history analysis. All are the same. Only this one direct integration, and I will show you also of the design procedure. Tall Building Initiative Guideline for Performance-Based Seismic Design of Tall Buildings 2010, developed by Pacific Engineering Research peer, and to propose PBD approach in Ethiopian e-government policy and as a guideline within the local consultants and construction firms. This is the objectives. Once the questions are answered, then for sure the objectives will be addressed. To answer these questions, what I did, the seismic performance of reinforced concrete, the seismic performance of reinforcement concrete RC3D model designed according to Ethiopian standard 815 2015 corresponds to Eurocode 8 2004 standard based on European norm 1998 1. This is the standard I am going to use. Seismic code recommendation is presented in this paper. In this study, two simple linear and nonlinear modeling 44 and 100 story were used. They are located in Ethiopian capital city Addis Ababa. So all the seismic maps and everything, I'm going to assume these buildings are in Ethiopia. And as I showed you, this is linear modeling, and I have also nonlinear modeling for the response spectrum and nonlinear time history analysis. We shall see also in the coming videos. So both RC buildings are analyzed with ETABS version 19 software with respective adopted codes. So this is the linear. These three analyses are for the linear parts, and two analyses will be for the non-linear parts. So these are basic type of analysis we have. For example, for excitation type static, and when the excitation type is dynamic, we have if the structure is elastic, this is also inelastic, elastic. When the structure is elastic or inelastic, the response, when the response is linear, non-linear. So the basic analysis type, for example, linear elastic static analysis, non-linear elastic elastostatic analysis, linear inelastic static analysis, non-linear inelastic static analysis, a lot of analysis, linear elastic dynamic analysis, non-linear elastic dynamic analysis, linear elastic dynamic analysis, non-linear inelastic dynamic analysis. All this kind of analysis can be performed, but for us the first one is linear and static analysis. We have that. Then we have non-linear dynamic analysis, we have that, and we have also non-linear static analysis. That is we have also. This is what we are going to do. So because the first are classical modal analysis, this is only for we will come why we are going to do this. Type of analysis performed on linear models. So as I told you, classical model analysis, response spectrum analysis, and linear dynamic time history analysis. We selected 11 ground motion from peer website was used. So this is what we are going to do. To match the selected ground motion with target response spectrum as per Ethiopian Standard 8 2015. Elastic spectrum type 1, we have type 1 and type 2 depending on the soil type. Both Seismomatch and ETABS version 19 software were used for this. The comparison parameter include maximum story displacement, inter-story drift ratios, shear force, overturning moments, and the fundamental period of the building for the first and higher modes. This will be the comparison. After we did the analysis, we will check. This will be the comparison. We can add others also, but this will be the basic ones. In addition to that, for all the three analyses, it has been we will check it. It should be checked, but it's already observed that the first two modes are translational modes. I will show you the first two modes. If the building is regular type, the first two modes should be translational, and the third mode will be torsional as required by different codes and guidelines. This also very important, because if the second mode, if the first mode is torsional, or then it is irregular type, or there may be some kind of problem in the building. This one I will show you in a minute. This is simple RC building linear analysis. As I showed you, we have 100 story and 44 story building. So it's kind of case study. So this work is original. This is novel work because this is our design. We can our material property, load combinations, whatever we do, target response spectrum we are using are just our work, and we can use different codes to compare with it, and we can do a lot of things with these two models. This is linear models, but we have also non-linear models. I will show you when we reach in other videos. So seismic analysis procedures, we have a lot of seismic analysis procedures. For example, linear static procedures, equivalent static analysis procedure. This is ELF, we call it ELF, equivalent static analysis procedure. I will not perform it for this. We can include it, but I don't include it now. Non-linear static procedures, this one is pushover, capacity spectrum meters and displacement coefficient meters, and various other pushover analysis meters are there, but capacity spectrum and displacement coefficient meters, this is very important. We will check we will see it when we reach there, because this is the 2 meters we have also in ETABS. linear dynamic procedures, response spectrum analysis, linear response history analysis, this is direct integration, and linear modal response history analysis, this one the concept of mode shapes, and this is direct numerical methods. Both methods are there in our option in ETABS. I will show you. Non-linear dynamic procedures, non-linear response history analysis, this is also the last part. This pushover is here, non-linear static procedure, this is non-linear dynamic procedure. So these two will be achieved after these three analyses are completed. So the result of this response spectrum, it's not included here, classical modal analysis, response spectrum, linear response history analysis, direct integration, or linear modal response history analysis. The result is the same, only the procedure and the procedure will be different, so we will see it also. This one, type of analysis performed on non-linear model. The non-linear static pushover methodology of FEMA 356 and ATC 400 requirements are then used to assess their seismic performance, and others also I will explain. Dynamic nonlinear time history analysis was used to validate the analysis result. Elastic stiffness, peak strength, target displacements, and plastic hinge formation pattern in the model are among the comparison parameters. These are the comparison parameters because we have this is the comparison parameters. This is sample building nonlinear. So as you can see, plastic hinge nonlinear model procedure. I use plastic hinge modeling, and when we reach there for nonlinear, I will make a video on that. Just let's concentrate now on classical modal analysis. This literature review. This is literature review. So according to one, prescribed code-based design cannot address earthquake design issues. The code-based method assumes the earthquake has a load, the material is elastic, and linear analysis was introduced and performed. But in reality, that is not the case. The nonlinear fields and behavior of the material, this is basic. The nonlinear field and behavior of the material are critical for proper analysis of a structure. Hence, performance-based design based on pushover and nonlinear dynamic analysis is recommended and adopted in different parts of the world. So as per this writer, this researcher, he also demonstrated that code-based design and linear analysis cannot address the earthquake design issues. This is the first point. Let's continue. So when we come to Ethiopia, we have the first Ethiopian building code, second Ethiopian building code, and third generation building codes. All of them are the same. As I told you, it's adopted codes. But when we come to seismicity, as a review of seismic hazard assessment and microzonation in Ethiopia, Guanin in 1976, he's a Canadian, produced the first seismic hazard map based on the probabilistic approach, which helped develop the first Ethiopian building code, ESCP, in 1983. As per his seismic hazard assessment, in 1983, the first generation of Ethiopian code was produced. It's adopted. However, his seismic hazard map was created by considering many destructive earthquakes, creating damage to social, economical, and human lives. Moreover, these two researchers in 1996 revised the map, and the results were updated for the second building code of the nation. This is also EBCSC Ethiopian Building Code of Standard 8, This was the second. Again, in addition to that, Modal ETL 1999, as cited by two, investigated the seismic hazard map of Ethiopia and neighboring countries by considering the site effects of rock at a regional scale of 10% of exceedance for 50 years. This is standard for most countries. Subsequently, the probabilistic seismic hazard analysis in Ethiopia and bordering countries included the poison earthquake source model and proper catalog declustering reported by Ayala 2017. Yeah, it was reported by this researcher Ayala. His name is Ayala. For 475 years return period, and to produce the third generation building design or code of Ethiopia. So as per concerning Ethiopia, we have 3 cores, but all of them are adopted. But for the seismic hazard assessment, Guanin has his own effort, but it has problem. Until now, the seismic map of Ethiopia should be revised, and a lot of research should be done. Literature review again. The recent appearance of high-rising building in Ethiopia raises concern about the country's existing seismic building code, design code, and construction policies. Ethiopia lacks its seismic design code and instead relies to European code. As I told you, this researcher also, he finds out that we have problem. Ethiopian and East African Republic is vulnerable to earthquake, though their magnitude is lower than other countries. The Rift Valley, which runs through the heart of Ethiopia, is a hot spot for earthquake and volcanic eruptions. Simultaneously, I will show you in a minute what does it mean. Simultaneously, more and more economically significant cities have recently arisen in this area. This would be catastrophic for developing countries such as Ethiopia, which are ill prepared for an earthquake like the one that struck EIT. So, furthermore, Ethiopia's last seismic code, Ethiopian Standard for Seismic Design, ES, Ethiopian Standard ES 2015, hereafter refers to ES 815, and other relevant building codes are based on European Standard EN 1998-1, which is equivalent to European Eurocode 8 2004. So we adopt it directly from Eurocode. We are using still Eurocode this or European norm 1998. This is a tectonic plates. This is a tectonic plates. We have a lot of plates. For example, this is African plates, this is South American plates, this is also Caucasus plates, this one also North American plates, Philippine plates. So we have a lot of plates. It's divided in different plates. This one we'll use for probabilistic the seismic map generation. We need to know which plate is there. This one is earthquake occurrence for the last 100 years. Just this one will give us some idea. These are the red ones are the places where earthquake occurred. So as you can see, this earthquake occurs in the plate's edge. That's how they divided the plates. So these are the past 100 years in the world this was recorded. Again, the East African rift system As I told you, this is Somalian plate, this is Nubian plate, this is Ethiopian plateau area, this is Red Sea, okay, this is the Nakul block, this is Arabian plates, this is the Rift Valley, this is the Rift Valley. I have another here. This is the Rift Valley, and this is the map, and this shows the earthquake, the depths of the earthquake which was happened. For example, this the blue one are depths of in kilometer, around 30 kilometer down from the surface of the earth, 30 kilometer down. This one is 20. This is the red ones are 10. Okay, this is the red one are 10. So in Ethiopia is this one. So the earthquake, most of the earthquake are happening in the Rift Valley area, and some are outside also. Okay, let's continue. Again, this is the given that the earthquake resistance of a structure is solely determined by their ability to survive in the plastic spectrum, it can be inferred those conventional approach to structural design focused on force are not right option. This force means just like adopted codes, because the shear force, we calculate the shear force, then multiply it with some kind of percentage, and we will distribute it like ELF design. So it's not this. As per this researcher also, he says design earthquake resistance structure assuming like force is not the right way. Performance based seismic design based on displacement is the seismic design philosophy of the future in the design of earthquake resistance structures. This is I am in favor with. Without the necessary improvement, the existing prescribed structural design code methodology from other countries will result in a significant catastrophe or failure. Performance-based design is a cutting-edge seismic design technique that has been extensively used for seismic assessment of existing structure and the seismic design of various new tall buildings. This is, we already discussed it a lot of times. This is our research also depend on this concept. So this researcher also they highlighted. Unlike prescriptive design method, the performance-based design offers a comprehensive methodology for measuring the performance of a building, device, or parts. So they are in favor of performance-based. Again, the studies in Ethiopia so far lack regional site effect or ground response analysis, topographic effects, groundwater response, and slope. This is for our seismic map generation. As a result, the seismic hazard map of Ethiopia to be accurate for seismic design of any engineering structures of economic cities need the detailed analysis on dynamic property of soil or local soil conditions, topographic and slope effects, water hydrology, active faults, slip plates, and fault lengths. All this should be included in the design. Okay, clustering and in the generation of PHS, probability hazard assessment or deterministic hazard assessment, and to come up with the seismicity map of Ethiopia. So all should be included. But as I told you, the first generation was designed by Guanin. He's a Canadian guy. He used some, because the problem is the data problem also, because we don't have a station. So he tried to get as much as he can. But now no problem. USGS, Peer, and other websites, we can extract the data anytime, whenever in the world, when there is any earthquake. Automatically there is stations, and it can be recorded and it can be used. But back in 100 or 150 years ago in Ethiopia there was no station. Even now we have 3 or 4 stations. I am not sure, but I will check it. But we have I don't know, 6 or 7 stations are there in Ethiopia now. Finally, further multidisciplinary investigations, logic 3 considerations are required to improve the map of Ethiopia. So still the map is, this researcher, he identified that the map has a problem. It's obvious. So if the seismic map and the zonation is has its problem, then the again adopting course will have a problem. The post 2010 design protocol in Manila, Philippines is based on the Pacific Engineering Earthquake Engineering Research Center Tall Buildings Iterative Guideline for Performance-Based Seismic Design from Tall Buildings. This is peer website. The output of the building for periodic earthquakes, 50% probability exceedance in 30 years with a return period of 43 years and very low failure probability for exceedance rare earthquakes. This is 2% exceedance probability in 15 years with a return period of 2475 years, is tested after the preliminary design is done according to the code-based design procedure. So the issue is now come to Philippines in Manila. They are using PBD, and after they design the building with a preliminary design, because performance-based design will be done after completion of the code-based done. So the code-based, the prescribed is base of performance-based design. So that's what it says. So this is a probability of 50 years with 2%. The return period is just 50 divided by 2%, around there. Let me 50 divided by 0.02, yeah, around 2475 years. So in Philippines also, this researcher already points out they are using. In recent year, the new seismic design term known as performance-based seismic design based on structural behavior based on displacement has been introduced in US also. So as per this researcher, not only in Philippines, US also they are using it. Even it was introduced from, the idea came from US. Again, the Great East Japan also earthquake with which struck on near Korea in 2011 accelerated the implementation of the construction protocol focused on seismic results. In recent years, several recommendations for evaluating seismic stability and reinforcing existing buildings have been issued. For some residential projects, a design method using passive energy dissipation systems. This is passive energy dissipation systems. Device is used for the new buildings, mainly residential buildings inhabited by more than half of the country's population. So they use passive energy dissipation systems. This is also very important in earthquake analysis, shock absorbers and others. However, the use of performance-based design for traditional style of new building is uncommon, since the prescriptive design technique still regains super in the field of building construction. Okay, regain supreme in the field of building construction. That means still they don't use performance-based design, because they are using still prescriptive design techniques, but they are using some kind of dissipation. We will discuss this also. This is due to lack of expertise and relevant information among civil engineers, and the fact that government officials are unaware of the critical need for PVD because Korea has never experienced many major earthquakes. This is also works for Ethiopia and most part of the world because we have lack of expertise on PVD, not only Korea. And the officials also, the government officials are unaware of critical need for PVD. This is very important point because it will work for us also. The design parameters used in nonlinear response history analysis loosely defined in Korean Building Code 2019 KBC, Korean Building Code of 2019. This is written, this researcher already point out that. So as you can see, in Philippines, in Japan, US, Korea, everybody, these countries are in favor of, only Koreans they are not using. A comparison of various structural engineering requirements from different countries' codes such as nominal load, load combination, load factor, resistance factor, structural engineering design philosophies, and material properties shows the degree to which one country code varies from another in terms of precision, protection, sophistication, and detail. So as I tried to discuss in the first part, even if this prescribed code, Eurocode, ACI, or whatever, there is also difference among these codes. And every year, every 2-3 years, researchers come up with a new idea and it will be revised and like UBC 94, then UBC 97, then IBC 2000. It continues like that. So always we are in the process of investigating another things, then we will incorporate it. So adopting a code from other country, even the code itself has a problem, because we will see in a minute different comparison works in different structures, RC, steel structure, bridges. A lot of works was done, but the code, one code will be maybe better or worse than the others. As per the researchers, we will see. So the adoption concept of code has a lot of problem, not by its own. Even the adopted code by itself is not the final adopted, because it is always revised every year. Much comparative research on the provision of various design codes can be found in the literature. New building codes, architectural philosophies, and material also depend on the empirical study between various countries' building codes and have more accurate results. The comparison of various design building codes, for example, Indian codes with Americans, the United Kingdom, and Europe, was reviewed in this literature review, in this paper. He did extensive amount of discussion about codes, the results, the outputs, economical aspects, the area of steel, the moment, shear, and all the member forces, the results he compared. So as you can see, the European was reviewed in this literature, reviewing, for example, Indian standard 456 2000, Indian standard 800 2007, again Indian standard 1993 from India, AC 710, ACI 31814, AICS 36010 from the United States, EN European Norm 1991, 1996 EC1, European Norm 1992, European Norm 1993, 2001, European course, European norms from Europe, BS, British Standard Part 1 and Part 2 from the United Kingdom are among the code considered. So I try to make it very short, but in his paper, this researcher, he make huge amount of comparison, and he discussed the whole idea of which code is better than the other. And in my research paper it is included here. In my research paper, in the literature review part, if I find in the literature review part, you can see it. No, sorry. In the literature review part, this researcher, he make a lot of research. Page. Yes. Yeah. This is a part. Okay. Yeah, this one, for example, this Murad M. Bakum ETL 2015, it compared the behavior and tolerance of various building construction codes in the USA, European and Egyptian. So these three were compared. And again in the second, this is the result, the output, everything he put it. Again, this Sami W. Tabash 2003 approved reinforced concrete design of structure based on ACI 318 and BS 810 requirement. So he did also this comparison, and the result also he gave his result. Which one? Again, Labani Nadi 2004 associate the strength design requirement of structural members such as slab, pillars and columns with different international codes such as IS 456 2000, BS 8110 1995 and European Code 2 1996. So there is huge, again, for Temple Newfor ETL 2015, they used Microsoft Excel spreadsheet to compare BS and ES2. They don't use any software, they use Microsoft Excel. Ali Abdul Hussein Jawad 2016, in terms of structural design standard, compare ACI 318 and BS 8105 and EEC 1992. So all these researchers, they compare prescribed codes, 6 also, 8 also, they compare using Procon. Procon is a software package, compare EC2 and BS 8110. Again, Ali S. Alim and colleague compare the structure effective of RC members using building shear. This is ACI and BS, and the result and everything is achieved. So the final one is evaluating the comparison reinforcement concrete member slab beam using various codes such as European code, American code, Indian code, British code, Canadian code. So the comparison of this building would aid in determining the most effective and cost-effective building code. The different criteria are found by these principles are determined in the diagram below. So as you can see, this variation of tensile reinforcement of beam, IS, BS, ACI, they compare it, and you see the difference. This is the difference as per the researchers. This is the difference. This is the main idea is, this researcher, he did a lot of research and he tried to show the difference codes. As per the extensive literature review, the adoption of the current prescribed design code approach from other countries will lead to the huge disaster or collapse of structure. We already discussed this so many times. If it is used without the proper amendment, even if it is amended, still it will not achieve the intended purpose as per our study until now. PBD is the state-of-the-art design tool in the seismic design, which has been widely used for seismic evaluation of existing buildings and seismic design of a lot of new high-rising structures. The conventional historical seismic design code apply the global response modification. This is R factor, everybody knows that. We just divide it by R, then we will consider for non-elastic behavior as important role in determining seismic design forces. Always we use this R factor. It depends on the structure, the code, and everything, but we will see it in the response spectrum time. The R factor accounts for the reduction of seismic force to predict the inelastic response of the building, resulting from the simplified elastic analysis method. Once we have elastic response spectrum, then by dividing it with the R factor, then it will decrease, because we cannot design for the elastic response spectrum, so it should be inelastic. The shortcoming is that the R factor does not account for the structural performance of component level and the seismic ground motion behavior. The elastic analysis procedure doesn't consider the redistribution of seismic demand in the various components of the building at the state of inelastic behavior under strong seismic evaluation. This is very important, because in the first question, in our research question, there was one question. It says why we are performing dynamic analysis while we have to increase the base shear acceleration we found from time history analysis or dynamic analysis to 80-90% of the base shear which was found from ELF analysis. The result is this one. Why we are performing dynamic analysis? Because the elastic analysis procedure does not consider the redistribution of seismic demand in various component level of a building at a state of inelastic behavior. This is the one, because dynamic analysis, when we will check the capacity and the capacity of the building in the component level. Each beam we will assign plastic hinge modeling, and we will capture the capacity of each joints, each column, each shear wall, and everything. Even in the same floor we might have different design, because when we assign fiber modeling for each floor, this is the main idea, because we will see the building as very tiny finite elements, and we are going to design each component level, so we will redistribute the force. That is the thing I understand from here. So that's why we can simply scale up the base shear acceleration, and we can use, but the main idea of dynamic analysis is it will go into component element level also. That is the thing. Okay. As per extensive literature review, adoption of the current prescriptive design code approach from other countries without the proper amendment will lead to huge disaster or collapse. This is already agreed. Performance-based design is a state-of-the-art tool in seismic design which have been widely used for seismic evaluation. This is also agreed. From the above literature review, we can observe that adoption of without the proper amendment will lead to huge disaster or collapse of the structure, despite the fact that code-based design has its own shortcoming, as we discussed. Again, adopting it without proper correction is not right. Even if we correct it, the seismic hazard map of the country, and we have to transfer from static analysis, linear static analysis, to non-linear, it should be the point. Especially in the context of Ethiopia, we don't have our seismic design code, and the seismic map developed and used for the zoning classification need to be checked for proper implementation and reliable seismic design. This is also as per this writer, he point out this. Now, gap in the existing knowledge. Why I am doing this research? The gap. Why this work is novel? Why this work is useful at the end of the day? The gap in the literature. From extensive literature review above, one can observe that there was huge amount of work was done on the comparison of design of structures in different countries' codes, and even performance-based design methodology was applied in different building types. There is a lot of work done in the performance-based or code-based comparison and a lot of things. But to our knowledge, none of them did intensive and comprehensive RC design on 44 and 100 story RC buildings, and included almost all type of design procedures such as classical modal analysis, RSA, response spectrum analysis, time history analysis in linear model, and SPO, pushover static pushover analysis, and nonlinear time history analysis on nonlinear modeling with plastic hinge modeling approach in one paper, and in the design location of Ethiopia also, because the geographical location also make your paper novel, because this kind of work never done in Ethiopia. And again, in one paper I never seen included all. I didn't see anyone start the analysis from classical model analysis, and I didn't see that. In addition to that, 11 earthquake data extracted from peer websites are unique for this paper. So I extracted 11 ground motion data for time history analysis and nonlinear time history analysis. These are also unique. This makes this paper novel and original and opens door for the future research works you shall come. Only in this paper which is not included until now is ALF, but in the future I will include it also to make it full paper. I will include ALF as well. Then this is the gap in the literature. None of there is thousands, 10,000, 100,000 works done in the PBD and other, but none of them was doing comparing and using 44 and 100 story buildings, and they include all the analysis types, and the location is Ethiopia, and the adopted the extracted earthquake data is 11 data are unique from peer website. So this makes this paper unique and useful in the future as well, and other researchers also might find it very useful at the end of the day. So this is the gap in the as far as this moment. That's what I found. So the methodology, methodology for this study: reinforced concrete RC moment resisting frames composed of 44 and 100 story multi-purpose buildings will be designed according to the specification outlined in the Ethiopian Building Code and PBD design principles. So as I showed you here, we have two models, original models, linear and non-linear, and we are going to perform our work in these two 44 and 100 story buildings. All the loadings, the reaction, the forces, everything we will see it in the moment. But in this video I am going to concentrate only on the classical modal analysis part. Both models are designed for similar loading and designing condition by avoiding geographical location difference, because they are assumed to be in Addis Ababa, Ethiopia. Subsequently, the seismic performance analysis made using a new generation of PVD methodology of nonlinear dynamic analysis, such that nonlinear response history analysis or nonlinear time history analysis. This is all the same, only direct integration method and modal, the classical model concept, we will see it. These are the core of PVD analysis using ETABS version 2019 software. This is the software I'm going to use. This is the buildings, 44 and 100 story buildings. PVD will be performed and others. For this paper, we will select and modify different ground motions for linear and non-linear response history analysis from peer ground motion database. Pacific Earthquake Engineering Research Center, USGS, and other websites, and Seismomage 2016, RSPMage, ETABS 2019 was used for our design sites. This is the methodology I'm going to use. And we'll compare and analyze the output of the comparative nonlinear dynamic analysis design output with Ethiopian code to check the output similarity and differences. Moreover, for verification of nonlinear static analysis, nonlinear dynamic analysis also will perform. The design procedure is peer, as we discussed, Pacific Engineering, Earthquake Engineering Research Centers. After the completion of preliminary design in according with code-based design procedure for both cases, the performance of the building is checked for serviceable behavior for frequent earthquake. 50 years probability of accidents in 30 years, and with 43 years return period, and very low probability of collapse under extremely rare earthquake. This is 2% of probability of accidents in 15 years. This one is in the Ethiopian building code, but now they incorporated also 10% in 15 years. In the analysis, finite element models with various complexity and refinements are used in different analysis using linear static, multimode pushover, and nonlinear dynamic analysis. Site-specific seismic inputs, ground motions are used to check the level of performance under the potential hazard, which is likely to be experienced PVD design methodology. Nonlinear dynamic analysis, this is the same, performed with existing Ethiopian design code and current Euro code, because the current Ethiopian code is adopted codes. Just to summarize, seismic analysis procedures. We have seismic analysis procedures. This is linear, this is non-linear. So structural mode, seismic loading, E, this is A, L, G, all are constant in linear. This modulus of elasticity, area, moment of inertia, everything is constant. That is why this paper is very important, because it is not constant. But in non-linear elasticity, you see modulus of elasticity or this strain, EI, K, stiffness, they are not constant. So we will assign this force deformation curves for each point in the nonlinear design step. We will see it. That's why each hysteresis curve we will assign for concrete, for beam, column, for hinges we will assign different capacity, and we have acceptance criteria as per the code, life safety, collapse preventions, and others, immediate occupancy. So all this will be discussed in the coming videos. Each will have its own capacity, how to calculate it, how to assign the force deformation curves for each point. So when we come to here, we have static, this is dynamic. So as I told you, we have equivalent lateral force, ELF procedure. This is ELF procedure. Again, this is a response spectrum analysis, RSA procedure, or mode spectrum analysis. This is sometimes called pseudo, because sometimes it's like dynamic, sometimes it is static, because mostly when the analysis is done, it is like static, but it is between dynamic and static, pseudo dynamic sometimes. And this one is modal response history or time history analysis procedure. This is modal response history or time history, all the same, because this is direct integration. This one we will use a concept of mode to calculate, but the result is the same. So modal response history or time history analysis procedure, modal RHA, this response history analysis or time history analysis, linear response history or time history analysis procedure. This is direct integration linear response history analysis or linear time history analysis. This is linear dynamic, this is linear static analysis we have. So only I didn't consider now ELF, but the others are included. Non-linear, we have several pushover analysis methods or non-linear static procedure. This is non-linear static procedure, and non-linear modal response history analysis or fast FNA, fast non-linear analysis, also included here, because it will use the concept of mode shape for the analysis. And this is the same, non-linear response history or time history analysis procedure, direct integration, non-linear response history analysis or time history analysis. So these two are the same, only the non-linear and this is linear. So as per our discussion, only this one will be included in the future. We will include it. So the tasks to be accomplished to meet the intended target as per our discussion, just I try to see the history of seismic design zoning map, how was achieved, what kind of study was implemented, probabilistic hazard assessment, deterministic hazard assessment, who did it in Ethiopia. As I told you, Guanin, he was from Canada. Basic seismology, an overview of the seismicity of Ethiopia, it should be checked again. Ground motion parameters, introduction to seismic hazard assessment, deterministic seismic hazard assessment, probabilistic seismic hazard assessments, all should be checked in Ethiopia. Again, introduction to seismic analysis and design procedures, equivalent lateral force procedure, ELF, as I showed you, we will include it in the future, not now. Response spectrum analysis procedure is included. Modeling for linear elastic analysis, already as I showed you here, we have linear modeling and we have non-linear as well. Selection and modification of ground motion record for linear or non-linear analysis of structure. I will show you how we will extract from peer website. For example, peer website, I can go directly online. And I can open the peer website, but we will discuss it when I come to linear time history analysis and non-linear time history analysis, how I extract it. We will see it. Okay. Peer ground motion database. This one we can go directly online. This is peer ground motion database. Directly we can go online. This is a database. We have two sites. First, you will sign in here. If you don't have, you will register. For me, I have already account, so directly I can go there. Takes time. Okay, this is my site. This is my email. I am professionalcivilengineer@gmail.com. This is it. Then I can sign in directly. I saved it already. Then sign in is successful. This is my email, and directly we can go to NGA West database. There is two type of database, but mostly we are using this one, NGA website. My network a little bit. Oh my god. Okay. Okay, this is a page. So we can choose no scale, this spectrum, and when we come there I will show you, but for now it's processing. In the time history analysis, when we reach there, how to extract, we shall see. This is a page, peer ground motion database. So RSN, this is a record station. If you know the record station, for example, for me, I think these are the record stations. If you know the record station, it's okay, or event name, or station number, or fault type. If you know the fault type, strike slips, normal obliques, reverse obliques, SS normal, reverse, normal reverse. If you know that, you can choose magnitude, for example 6.5 until 7.5, RGB, this RGB, June and Bohr coefficient, June, RGB. I will show you what does it mean RGB. I already included there. These two researchers, the distance between the fault and the earthquake and the projected length will be RGB and R rupture. This is RGB and R rupture. So if we give the distance, we can find, and I will discuss this one when I reach this part also. This is just for you. V30, VS30, this one also you can give pulse, any record, maximum record, for example 3, 4, whatever you need. Spectral ordinates, SRR, this SRSS, or anything you want. Damping ratio 5%, average, or whatever. Then once you put this one, you simply search record. Search was successful, created. Please allow me to generate the graphs. As you can see, so as per our criteria, this is the pseudo, this is a period, this is spectral acceleration, and if you go down here, you see, we, as per our criteria, we have this one. So result shows 1 spectral ordinate, SRSS. This is also SQC, and we have 3 kind of record station 164. A scale factor is 1. This one D5, D6. This is aerial intensity, event, Imperial Valley 06, year 1979, station 0 Pareto, magnitude 6.53, mechanism strike slip, RJB, R rupture, everything is written here. So everything is written. If you need it, then you can download it and you can use it. Download it like this, but we have to download it like time series record. Okay, then by doing so we can download. As I showed you here, I already downloaded 11 for time history analysis, nonlinear and linear time history analysis. I already extracted here ground motion, pure ground motion. This is 4. These are the data I extracted already, and 7. This is 7. So we will use this data. We will scale it, and scaling and matching of this data we will do it when we reach time history analysis. For now, this is a simple step just for demonstration. So selection and modification of ground motion record for the linear or non-linear analysis of structure, linear response history analysis of structure. This is the first. Introduction to performance-based design approach, structural performance level and acceptance criteria. This will be also done in the non-linear part of our series, and we will see what is the 3 levels. We have 3 levels: life safety, immediate occupancy, and so this will be 3. We have 3 levels. Okay, nonlinear modeling and behavior of building structure, fundamentals of nonlinear modeling, distributed and lumped plastic approach. We will see also aesthetic behavior. This is very important. As I told you, the aesthetic behavior of steel, concrete, we will see it, and the fiber modeling approach and plastic hinge approach. This is the 2 approach we have, and the procedures, how we will do it, the hysteresis map, and force deformation curves, everything we will see. Nonlinear modeling of various structural components using ETABS. This is the same as this one, because plastic hinge modeling and fiber hinge modeling. This is the 2 parts I use, but there might be another also. Nonlinear modeling of various structure components using perform 3D. Nonlinear static analysis of the building, pushover analysis, static pushover analysis procedures, pushover analysis using ETABS, and perform 3D. For this purpose, until now I am using ETABS, but in the future, when I have time, I will perform this design using perform 3D, and we will compare the result also with ETABS and perform 3D also. This one also one point to make this research novel, because the result of ETABS and perform 3D will be compared and analyzed. Nonlinear time history analysis procedure using ETABS and perform 3D, as I said. Interpreting the dynamic response and seismic performance of a building, understanding the analysis result from nonlinear time history analysis, service level and MC level, maximum and dB level will be checked. So all these proposed reference to be used. This is very important textbooks, and this will be referred, and supporting documents also. These are FEMA, ATC 400, this ATC 40, AC 4113. Now we have 17 also. We have 17 now. I am using 17, but in ETABS we have 14, again 17. Both we have, especially for this performance levels. I will concentrate on this one. Council of Tall Buildings and Urban Habitat. Recommendation for seismic design of high building also there. PEER, as I showed you here, PEER website, ATC 72 modeling, ASC 716. There is 17 also, as I told you. This is 13, this is 16, 716. There is ASC 716. So we will use all these guidelines, videos, very important videos for PVD and other internet resources. As I told you, USGS peer ground motion database, this one we have seen it now. This is a peer ground, and we can download Cosmos, KNet, and this also. All are useful. Supporting document, these are supporting document, magazines, articles, and everything. So at this point now, we discuss what is the importance of my paper, what I am intended to do, what is prescribed code based, and the seismic map difference problem of Ethiopia. And I discuss a lot of issues, why this paper is very novel and original. And for this paper I prepare already linear and nonlinear modeling for our work, and we are going to perform 5 analysis types without ELF, only ELF, but we can include ELF also in the future, but this is what I am going to do. So as per our discussion, this is huge work, as you saw it is very huge work, but we reached this point also very nice. So linear dynamic modeling part 1, we are going to make classical modal analysis for 44 story RC linear sample model, and classical model analysis for 100. In this video my idea is to cover this part only. Then I am going to prepare another 5 videos for response spectrum analysis for 44 story and 100. Then the result will be checked. This one also, the time, the fundamental time, and the frequency, and the first mode, second mode, third mode, whether it's translational, torsional, is there any problem, we will check it. Why we consider classical model analysis, response spectrum analysis. So RSA 44 story, RSA 400 story, we will check it. We will see the result for overturning moment, local response, global response, everything will be checked. Okay, moment, shear, all will be checked, and we shall see the fundamental time also, period also will be checked. Linear dynamic time history analysis for 44 and 100 story, as we extract already 11 ground motions, then we will scaling, matching to our target response spectrum, design response spectrum, how we are going to match it, we will see it, because that is also another part. Seismo match also has, and ETAPS also has matching criteria, and with time domain or frequency domain, we will match the real ground motion extracted, and we are going to use it for our building design purpose, and we will check all the responses and the designs when we will compare it with response spectrum and modal analysis, and there is discussion and findings. We will continue. Again, in the second part, we have nonlinear modeling. This is linear modeling. We have nonlinear modeling. Then in the nonlinear static analysis, pushover analysis, and nonlinear time history analysis will be performed, and we will check the result as well, and we will compare it with the result of linear analysis, and we will see what is the difference, what is the shortcomings, and like that. So this is the first part 1, classical model analysis. This is the free vibration analysis. This is the result. I will show you, because we have the fire also. This is 100 story. Let's open 44. I think this is 100, will take a lot of time, so let me open. Just demonstration purpose, I will show you the result. This is 44-story building. Both the ones. Okay, let's back to here until it opens. This is classical model analysis, and we will see the mode shape: first mode, second mode, third mode. For this, I set it 20 modes only, but basically modes are equal to the number of degree of freedom of your building, but no need, because the higher modes will not contribute into our discussion. So free vibration analysis definition: natural vibration of a structure released from initial condition and subjected to no external load or damping. As you can see, we have main governing question, eigenvalue problem. We have this one, so we don't have any external load applied and we don't have any damping. So damping term and external force application here in our building, there is nothing here. Okay, this is why free vibration. This is free vibration. Once any engineer who first design his buildings, once he finish his modeling, then he should perform classical model analysis to check the health of the building. We will see that, because for classical model analysis we need only mass matrix and K matrix. M and K matrix we have, then we don't need. Okay, figure 9, free vibration analysis model. The governing equation of motion solution gives us natural frequency. We will get natural frequency and associated mode shapes: first mode, second mode, third mode. As I told you, the first mode and second mode, if it is a regular building, we have to get translational, pure translational modes. We have to get pure translational modes. The third one will be rotational. This is for regular buildings. If we have some problem, I will show you in a minute, that might not be the case. So as insight into the dynamic behavior and response of the structure, this is an insight. It is very we will discuss now. Natural period of end frequency or frequency, the heartbeat of a structure. As I told you, classical model analysis is like a heartbeat of a structure to check the structure is healthy or not. If there is any problem in if we have local moment or other things, we can identify. Indicates the stiffness and mass relationship. Only M and K we need for this analysis. And basis of damping, resonance and application effects, because this is a basic point. Once we know the natural frequency and period of time, none of the forced modes and periods should be the same as this one. If the period and the frequency of the result of classical model analysis is the same as the forced one, then we will face resonance. It will amplify. We will come. I will tell you. Many relationships are there for tall buildings. If you have number of stories, then 0.1 times number of story, it will give you the fundamental period of your buildings. The fundamental period of your buildings. For example, this one is already run. Okay, this is already run. Okay, let me finish that and I will show you in a minute. Mode shapes, we will check the mode shapes. A mode shape is a set of relative, not absolute, modal displacement for the particular mode of free vibration for a specific natural frequency. There are as many modes as I told you, if you remember, there are degree of freedom. So the modes are equal to the degree of freedom. Not all of the modes are significant. As I told you again, as per the code, only 80 up to 90% are more required. So even if, for example, for this one, I just assume 20 modes. I can show you. Define load cases. This is the mode. This is modify. You see, this is 20. Maximum number of modes for this analysis, I use only 20. But 20 modes are not required. Only maybe 4, 5, 6 modes may achieve 90%, 80 up to 90% of the modal mass participation can be achieved. 80 up to 90 more required. So local modes may disrupt the modal mass participation. Loosely connected structures. This is very important, because if we have loosely stiffness or something, I have one video. Wait, let me show you. For example, I have one video here. So let me close the volume. I want to show you. Yes, I want to show you this guy video. What is local mode has a problem. I want to show you that. This building, for example, is there now. For example, if there is local mode, I will show you in a minute in our building, but this is, for example, 10% and 63.63% are there. So wait, how local modes have a problem, because this point I want to show you, because we will yeah, you see, when we have a local mode, the mass participation factor will be will have problem. Why this happens? Because of stiffener or something. Then if you have local mode, the first mode and second mode might not be translational, and the third mode will not be torsional. As you can see, all the buildings are fixed, but only these parts are moving. This is because the problem will be, as you can see, here. Yeah, you see, this is what I want to show you. Okay, this is what I want to show you. This is all 0.01. So that's why the problem comes. So when we come to our so that's why local mode, these local modes may disrupt the modal mass participation, because the first mode and second mode should be for us, for example, we can go here. This is our building, and this is already gone. I will show you in a minute, but we can go display, show table, for example, structural outputs, we need modal information. Okay, no need the design. Structural output, base reaction, okay, but I need more information only. If I open, this is the mode information. Okay, for example, if you go to this modal mode participation, as you can see, we have UX, UI, UZ. So as you can see clearly, 70% of the mass of our building is in the UX direction. That means pure translation. Again, second mode is 71.73%. This is pure in the Y direction. So in our case, mode 1 is 70% in the X direction, again in the Y direction. Then the third one, you see, this is only 1%. That means this is Z. U and X are 0%. Okay, so this one is almost 69% in the R direction. Again, mode 4, mode 5, mode 6, it will continue. But as per computer programming, what does this one means? Mode 1 means this is the first mode in the X direction. Mode 2 means this is the first mode in the Y direction. Mode 3 means the first mode in the Z direction. 4 means the second mode in X direction. Again, 5 means the second mode in the Y direction, and 6 means the second mode in the Z direction. 7 means the third mode in the X direction. Again, 8 means the second mode in the third mode in the Y direction, and 9 means the third mode in the Z direction. It will continue like that. And if you see the sum, almost 89.8, almost 90% is already achieved in the tens. That means almost in the third mode, the 90% is already achieved. That's what we need. There is no need to include all modes. Even if I use 20 modes, there is no need to use all 20 modes. Okay, so that is what it means. That is what it says. Though we can see all other reports, participation factor, the period also. You see the first mode 3.95 second, in the Y 3.7 second, in the Z 3.4 second, and we can see also this one now in the animation. All this one, frequency, everything is, we can see here. So we can check this also by animation. So we can go here, the mode shape, this is mode. So the first mode was in the X direction, so apply. So we will apply it and start animation. This is mode 1. It will take time. Let me close yeah, let me close the volume. So as you can see, this is the first mode. This is the first mode, 3.95 second. This is a period, and it is pure translation in the X direction. In the X direction, the same what we see in the table. Again, we can see the second mode. This one I can show you in a little bit. For example, let me add one window. Let me add one window, and I will show you in a section also. I have a video I will show you. Just this is for the first one. Then I have 20 modes, and for the 20 modes I have a video while it opens. Okay, it needs this is one of the limitations one of the limitations, because I have to use perform 3D. If we use perform 3D, it will not, especially for linear non-linear time history analysis, it will take more than 10 or 20 hours. Once I start the analysis, I will put the laptop and I will sleep. In the morning still it is running. Sometimes it will crash and we have to start again from the beginning. So that's why perform 3D should be used for especially non-linear analysis, and the specification of the laptop will have some effect. So but I prepare already the videos. We will see it in a minute. Okay, this one I already, let me make this one elevation 44. Okay, no, I want to open elevation. This one also, mode 1. I want to show you with elevation this side. Then start. You see, this is in the X direction. Now I want to show you this one, the second mode. It was in the Y direction. In the Y direction. Okay, until it comes, let's go to our discussion. So local mode, we already seen, we have seen it. Modal analysis. The modal analysis determines the inherent natural frequency of the vibration. As we can see, we will see the natural frequency and the fundamental time we will find, because at the end of the day we will check for resonance. Each natural frequency is related to the time period and the mode shape. Mode 1, mode 2, mode 3, mode 4, it will continue like that. Time period is the time it takes to complete one cycle of vibration. The mode shape is normalized deformation pattern. This we can't normalize it. It doesn't have any significance. And modal analysis, the number of modes is typically equal to the number of degree of freedom. We already discussed that. The time period and mode shapes are inherent property of the structure and depend on the applied load. The modal analysis should be run before applying load any other analysis to check model and to understand the response of the structure. This is very important. This is why this paper also unique, because before applying any kind of analysis, modal analysis should be performed and the natural time period and frequency should be identified to check the resonance problem in the later stages of any design. Modal analysis is this is predecessor to most type of analysis, including gravity load analysis, response spectrum analysis, time history analysis, pushover analysis. Everything before doing any analysis, this is the first analysis we have to see, because if we don't know the time history, if we don't know the health of the structure, as I showed you, if there is local problems, local modes or any other things, we have to identify it now, and in the later stage we have to check whether we have a problem, a danger of resonance or something. Modal analysis is a useful tool even if full dynamic analysis is not performed. Before it's performed, it's very useful. Modal analysis is easy to run and is fun to watch when animated. Application of modal analysis: the time period and mode shapes together with animation immediately exhibits the strengths and weakness of a structure. Modal analysis can be used to check the accuracy of a structural model. The time period should be within a reasonable range. As I showed you, 0.1 times n, number of stories. It will give you the time. For example, for us, we have 44 story. Yes, 44 story. So we have 44 times 0.1. Yes, so it is 4.4. The fundamental time is 4.4. But if you go here, you see the second mode, it is around 3.7, but the first mode is 3.95, so 4.4. the period is around that. So as you see, this is the second mode. It is pure translational in the y direction. Then the third mode should be torsional. This is why we have to perform. That's why it will tell us the time and the resonance, for example, and the disconnected members are identified. As I showed you first, if there is disconnected members, everything should be checked at this stage. This is a chance we have to check our building health. Local modes are identified that may need suppression, because if there is any local mode, we have to check it. So the video and some of the lectures what I am using now, I found it from this performance-based seismic design of buildings, spring from Fuad A. Najim. He's professor. I use some of his concepts. His modal analysis. The symmetry of the structure can be determined. The symmetry for doubly symmetry buildings, generally the first two modes are translational and the third mode is rotational. If the first mode is rotational, the structure is unsymmetrical. This is what I want to show. This one, you see, this is the third one. This is rotational, and the period is 3.46333, and the same thing I can show you. For example, this is the, let's go here first. So if the first mode is rotational, the structure is unsymmetric, but our structure is symmetrical, so the first two modes are translational and the third mode is rotational, so we are safe. Our building is in a good range. The resonance with the applied load or excitation can be avoided, because none of the higher modes, once we apply any loading, the fundamental time and natural frequency should not be much with this time and natural frequency. If it happens, then we have a danger of resonance. The natural frequency of a structure should not be close to excitation frequency. Yes, any excitation frequency should not be close to this one. So this is a formula we have, 2 pi over m over k. This is the fundamental time. So as you can see, for classical model analysis, the only thing we need is mass matrix and k matrix. No need. That's why any engineer, as a best practice, once we completed the modeling, then we have to continue with checking, applying classical model analysis, then we will know the time and the natural frequency. M over k is equal to 2 pi over t. Then we will check it. The most important reason for performing classical model analysis is to compute the shape and frequency at which the structure will amplify the effect of dynamic load. None of the forces, the forced vibration modes, should match the natural frequency of the structure to avoid resonance and amplify the effect of dynamic loading. This is very important because it will amplify the dynamic loading. So once we know that there is local modes or any loading, if the forced frequency or anything match with the natural period and time, then we have a danger of resonance. So this phi means the shape, mode shape, this natural frequency and period values gives us useful information about the expected dynamic behavior of our structure. A very first thing we should do after we complete computer model is to run the model analysis, or the eigenvalue analysis. We call it eigenvalue analysis because the procedure is long. Then the software will calculate mode shapes, time period and natural frequency of our structure. Hence this value should be within a normal range. As I showed you, 0.1 times n again determines the principal direction of a building, which coincide with the first and second mode direction. Then later or RSA and time history analysis should be performed in this direction, because it will tell us, once we know the first mode, the second mode and the rotation, then these principal directions should be used with this one. So just to show you once again, display, show table, this is outputs. So as you can see, even in the table form, mode directions, mass participation of mass result, as you can see, the third mode is translational. This is the first mode, 70%, 71%, and the third one is torsional. So this is how we will check. So we can go the higher modes also. I will show you the higher modes. For example, for this one, let's go and see. For example, we have 20 modes. So let's check for 20 modes how it looks like. But I have a video I will show you also, because this one is a little bit this is the 20s mode is like this. Start this one. I can close it now. Okay, until it comes, let's back. So we are okay now. So why we make classical model analysis? What is the secret behind? This is the heartbeat of a structure, the fundamental period, time, all these things are assessed here. That's why we start our paper with classical model analysis. So this is the results: first mode, second mode, third mode, as I showed you now. This is the third mode is translational, the second mode is in the Y dominant structure, the first mode is in the X direction in our case. So this one also just the modal analysis, as I showed you here. The 90% of the mass participation factor was achieved around 11th point, mode. So no need to, even if we have 20 modes, no need to compute 20 modes or 50 modes, because I will show you in the 400-story building I use 50 modes. So no need to add up 50 or compute all because we need only 80 up to 90% of the mass participation factors. So this is the modes as I showed you. The first mode was 3.806, frequency is this one. Then the second mode was, in our case, was in the Y dominant direction, so 3.58. Mode 3 3.27, this is torsional. And the last one, mode 20, the period is 0.136 and the frequency 736. As you can see, the frequency is increasing from mode 1 until mode 20. The frequency is increasing, the period is decreasing, as you see. So this is also one thing we will see. This is period. This is mass participation factor, as I showed you, 71% of the mass in the X direction in the first mode. The second one is 72% in the Y direction. It will continue like that. It will continue like that. So here it will continue like that. All this, the mass are here, around here. 90% is reached already, 8 or something, 7. In the 7th mode we already reached there. This is for 100-story building. The same thing I will show you. 100 building also the same thing. This is the result we have get. So response spectrum analysis will be done in the next video. This is only for the first one, but let me show you the other one. For example, this one, this is 20-story. This is 20, the 20s mode. The period is 0.145 and it's really vibrating because the frequency is increasing. This is how it goes. And just to make it, this is a 20s mode, but I have the video, as I told you, because this is classical model analysis, 44 story. Then output, I have video. So as you see, I have 20 videos and I have the animations also. Let me open it from starting from first mode. This is the first mode. As we have discussed, this is in the X dominant pure translation in the X direction. Around 71% of the mass was participating in the first mode. And we have also section, all the same, but section. This is the first mode, just to show you. If we go to second mode, it is pure translation in the Y direction. This is in the Y direction. So as you can see, it's in the Y direction. I recorded this one, and this is also the elevation. If you go to third mode, this is torsional. This is torsional. So the main idea of classical modal analysis is to check the health of the building, the natural periods, if there is any local modes, if there is any problem in our buildings, stiffener problems and other problems. We can check our building. Once everything is okay here, and we will identify if there is any resonance problem or not, then that is the main idea. So this is the third, just to make it the fourth. Fourth means the second mode in the X direction. So the software has its own reading. You see, this is the second mode. This is the second mode in the X direction. Again, this is elevation. You can see this will, you see, it will cross once only. So all this one you can see clearly. Okay, the fifth mode. The fifth mode means this is the second mode in the Y direction. This is the second mode in the Y direction. This is the second mode in the Y direction. It will continue like this, only the second mode. If you want to see, you see, this is the second mode in the Y direction. Only cross once. Again, 6, we have torsional, the second mode in the torsional. So it will rotate. This is the second mode. We can see here it is rotating, you see. Then let's go to 7th mode. This is the third mode. It will cross 2 times. This is the third mode in the X direction. This means the first mode, the third mode in the X direction. It is 2 times cross the vertical line. You can see this here. You see, this is the third mode in the X direction. Then this one in the Y direction. The same thing but in the Y direction. Now we are going to the higher modes, you see. This is the third mode in the Y direction. So the higher modes, the frequency is increasing, but 9, you see, torsion, this is torsion, 10, it will continue like this. For example, 14, you see. So you see, it is the higher modes, the frequency is increasing. Let's go the final 20s mode, for example. This is a 20s mode. This is for 44 story building. Again, I will show you 400 story building. This is for 20 story building. Okay, 400 story building. This one, output, videos. The first mode, as we discussed, it should be pure translational. You see, pure translational in the X direction. Pure translational. And I will show you. Yeah. And the second mode, again pure in the Y direction. This is also pure translational in the Y direction. I will show you in a minute with table form also. And the third, you see, again the third will be torsional. This is torsional. This is torsional, as you can see. This is torsional, and the force, this is the second mode in the x direction. The second mode in the x direction. You can see also, and we can continue like this until the higher modes. For example, we have 49 modes, 50, but I make it 49, the record, but I will show you in a minute. This is a higher mode, you see. This is a higher modes. So classical model analysis is very important for the health of the building, and to know the natural frequency and period, and to check the local modes, moments or anything if there is, we can, for the stiffener or something. This is clearly, you can see the higher modes. This is the higher modes. So to see this in software, let me stop this one. So this is okay, this one okay. So now let me open 100 story. This is 44 story. So classical model analysis, EIT 100. So until it opens, let's go here. So as per our discussion, next video will be in the response spectrum analysis on both. So we'll continue like this, and we will going to have 5 videos, and we will see each in detail, and this Seismo match also until it opens. Wait. I was searching for until this one opens. Where is it? I have here. Until it opens, and let's move it from here. Because this is 100 stories, that's why it's creating problem. This one, Seismo soft, Seismo match, yeah. This one. Here. Here. I was searching, but it was here. Okay, it opens or not. Once it's open, I will show you. But this one, this is Seismo match. I didn't see it. This is Seismo match. Once we extract the data, we are going to match it here. How we are going to match it, I will show you. This is Seismo match. This is also student version. For example, open single. Just this is an highlight, but we will discuss it deeply when we come to the third video, time history analysis. For example, it has its own data, but I am going to use my own data. EIT, I am going to use the data from time history analysis. From here, pure ground motion, for example, let's go okay, open all data. For example, let's choose lenders. This one acceleration, this is displacement, this is velocity. So we have three datas. For example, this is station 147, this one is 237. So each data has three datas: acceleration, displacement, and so if we go for lenders, for example, the same AT2, DT2, VT2, this is a file. So let's go this file. For example, this is a file. So first line 6 1 2 3 4 1 2 3 4 5 6. No, for example, no problem, directly I can say pure format. Okay, then the first line will be, because we have a lot of formats, no need to count, we can go for pure NGA format because that's where from. Then the last line, because it is counting with line, total point is 11,176, time step 0.05, scaling factor 1, and time step is the same. This is 5, means 1 2 3 4, because the first 4 are words, then it will start from here. Then once it is okay, frequency, initial value skipped, we don't have any, then we can say okay. So you see the data directly comes, acceleration with time. This is the real earthquake data, but this is a student version which I have, so it will work only for matching. For me it will work only 4 seconds, more than 4 seconds it doesn't work, so that's why I will go for ETAPS. So here this is the data already comes. Now define target spectra. Now we have to define our target spectra. So directly we can select from the code. For example, for me, as I told you, Eurocode is the adopted code, so we can use that one, or European norm, EN recommended. A spectrum from load, acceleration, damping, you can put always 5% is and load spectrum from file, or if you want, but we can use this one, elastic elastic spectrum design in elastic, if you want to design in elastic. Damping is 5. Then this is the peak ground acceleration. For us it is 0.1, you see, around 0.3. this is our and this is only 4 seconds, you see, because mine is a student version, it will not go above 4 seconds. Once it's okay, then the ground type A, B, C, D, you can name, for us is B. Importance factor 1 2 3, it's as per the code, then you can say okay. Then this is your target response spectrum. As you see, it is only 4 seconds for me. Then minimum period, then scale factor, maximum period, tolerance, this is as per your need. Then you can say do matching, then it will start matching. it will start matching. Yeah, so once it is matched, it will show you here. Then total progress by accelerometer, then acceleration progress. Okay, then you see, so this everything what we have here, this is the Lander's earthquake data, RSN 375. Then this is a matched data, match acceleration time history data as per our need. So as per the code, from 0.2 t until 2.1 t, the matched data should not be down from the target response spectrum. If the data will down, then we will not use this data. So we will discuss this next. As you can see, it will separate it: acceleration, velocity, displacement. Once we have the acceleration, then matched accelerogram also here, comparing time series. This is a comparison. This is original acceleration value, the original we brought it. Then this is a matched one. You see, this is a matched one, the velocity also and the displacement also. Here a big difference, like that. Response spectrum, you see, this is target spectrum. The target spectrum is this one. Then the matched one is this one. This the original accelerogram is like this, the original. Then the matched, you see, the matched one is like this. So as per the code, the matched one should be always greater than, more than 90% of the target response spectrum. So that is what it is. So the comparison is like this. The spectrum from original accelerogram is this one, and the spectrum from matched accelerogram is this one. So it's good because this one is already, I choose it, but sometimes it will come down something, so you have to choose what, as I showed you from peer ground motion. When you here in the peer ground motion database, you have to fill all the requirements as per your site, the response spectrum, the value, VS, while, Bohr, J-Bohr, all this data has effect. So once it is okay, then if it is in this above 90% from 0, we will discuss this in detail next. And we have table also. If you want, you can take it in table, you can copy and you can draw. This is parameter from matched acceleration. This is original accelerogram. Again, we have the mean also. Okay, calculate mean, save mean. Now calculate mean. At least okay. Okay. We have to select here, calculate mean. This is a mean. This is the original one. This is the mean one. So ground motion parameters: maximum acceleration, maximum velocity, displacement, all are here. Cumulative, everything. So this is a highlight, but we will continue when we come to time history analysis. We will see how we use this, because this is the student version, only until 4 seconds is allowed. After, but for us, let's go here. For us, the first mode is 9 seconds. So this one is only 4 seconds. It works only 4 seconds. But for us, we need, especially for 100, because 100 times 0.1, 10 seconds minimum, the fundamental thing. So we need that. This one, I don't know why it's not opening. Okay, it's open. So until it opens, just to stress the point, this is until 4 seconds, but for us we need additional. So let me close this one, so let me close this also. Do you want to save? No, this one is taking time. I want to show you maybe table if it's open. Okay, I need only the table one. Okay, so we saw the first and the second is the pure translational, and the third is torsional. So I want to show you here also in the table form. In the tabular form, but I don't know, the computer is not responding. Let me close. Okay, it crashes. Okay, let me open it again, just one more time. So until it opens, so this is next time we will continue from response spectrum, this one, part 2. So if it opens once, I want to show you. You already saw with the video, but so the whole research paper is this one. The whole research paper is this one. All the literature reviews, the analysis. Okay, it opens. Let me try once. Okay, open. Classical models. Yes. Okay. That's why at the end of the day I want to do this analysis with 3D perform, because 3D perform is good for especially nonlinear analysis. Until it opens. Okay. Okay, thank you. It's already opened. Okay. Okay. Now what I want to show you, display table, this one, structural output. I want to show you modal informations. No need this other outputs, center of mass and other things we don't need, and base reaction also we don't need. Please wait. Yeah, it's because 100-story building, it's a little bit heavy for my laptop. Okay, so already took a lot of time. Come on. My god, that's it. Okay, anyways, as you can see, the first mode is 99.9% in the X direction. Again, the second mode is pure translational, 100% in the Y direction. And this one, as you can see, RZ, this is completely torsional. So as like this we can check. So we can see also mass participation factors. You see, 68% of mass was participating. This one, 69.72, 0%. You see, in the here, and RZ, where is it? RZ 75%. So in this way, we can check. So this will be the end of this session. We have the next 4 videos, and we will continue. Thank you.